Okay, looks like we are online. I'm seeing the YouTube section online. I'm not sure what's going on with the LinkedIn. So sorry, Al. Welcome everyone to this episode of Hoot. We are here to talk about BGP and Cilium today. So thanks everyone for coming along. We will share show notes at the end of the show. And with me, I have Daneyon. But before anything, let me just share my deck here. Present, share screen. Okay, all right. So welcome everyone again. My name is Marino Wijay. I am a platform advocate / developer advocate at Solo. I've spent a lot of time in the networking world and, made my way into the world of cloud native and Kubernetes and spent a lot of time, understanding how container workloads run, how they network, how they get around the network to speak with other artifacts. And it's just so funny that BGP just re-enters the chat and the conversation when it comes to Kubernetes, and that has me all excited. About a year ago, I was testing out Cilium's BGP functionality before some of the most recent advancements in the last year, and it was pretty interesting to be able to get it up and running, but it was not the ideal approach. And I think the Cilium technology has come a long way. So pretty excited to dive deep into BGP configuration and use cases and show you all how it all works in Cilium. Over to you, Daneyon.
Thanks, Marino. So my name is Daneyon Hansen. I'm a principal software engineer here at Solo. I have been involved in CNCF and Kubernetes since the early days, and either as a contributor or a maintainer of several different projects. I think for about 4 months now, I've been focused in on Cilium, specifically around the BGP control plane, which we'll be diving into here shortly. Marino, you're on mute, I believe.
Oh, yeah, thanks. That always happens to me. I've got a mute on my microphone here, and I'll forget that I've hit that button, and then I just talk into the mic. But anyways, I was just getting into a bit of a BGP recap here and talking a little bit about what it is as a protocol. So for those that aren't familiar with it, it's a routing protocol that's widely used in enterprise service provider environments where you've got massive scale going on and you're using this protocol to help share networks to other networks. So every object should be able to find another object in that network. Now, BGP operates as a routing protocol that uses this path vector algorithm that effectively looks for the shortest path in your network. Now, you can take BGP and you can influence it so that it takes alternative paths, and we'll talk about why that might be the case. But just to kind of recap some of the other capabilities, BGP comes in two flavors, either internal BGP or external BGP. Now you might be wondering why we have two flavors. There might be situations where if you look at this diagram here, you have routers that live inside of a network, and they're part of what we call an autonomous system. So this is your boundary of networks here, and you may not see a line. Actually, this might be a better example where you're seeing this IBGP peering between this router here and this router down here. Now, the IBGP peering simply just establishes that all of these routers are on the same network, but there are some other considerations around using IBGP where it is not as believable of a route when it injects routes into the routing table, because there are other routes that might be more preferred. You might want to use a different routing protocol within your network, and then use BGP on the external when you're peering with external networks. So with eBGP or external BGP, we've got peering between different autonomous systems. And one of the main reasons we want to do this is we actually want to cut back on the number of routing updates we feed to our eBGP peers. Imagine if there's a lot of routing or networking that changes in a given location, we may not always want to communicate that to the outside world or to other networks. And only this might be the main reason behind this is because we also don't want the situation where links go down and then come back up just because of a route reconvergence or a route that happens to pop into the table and then suddenly disappears. So we want to be able to control how we share information with our neighbors in our BGP setup. So one other thing I'll point out is between routers, everything is considered a neighbor. So between these two routers, this is a neighbor-peer relationship. So this router is a neighbor of this router. And between the two, as long as they're configured for peers of each other, we'll exchange network information or network route information. Now, there's a few things to also consider on that neighborship establishment. There are a few phases that we want to consider. There's the idle phase, there's the connect phase, there's the active phase, and then there's the established phase. For troubleshooting purposes, when you're considering why I might not be learning routes, it may be due to the fact that you're not sitting at the established stage where routes can be exchanged between neighbors. It might be sitting at the active stage where the peer might be defined, but there might not be any sort of TCP connectivity, which brings me to how BGP functions. So BGP uses TCP port 179, and you can also define other ports if you want to be able to form neighbor relationships or peer relationships with other BGP speakers. If, for example, there is a firewall that is blocking these two peers from speaking, you're likely because it might be blocking TCP port 179, and your state might be set to active. So until you create a firewall rule that allows bidirectional communication on that port, the neighborship might not be formed. BGP itself isn't just limited to, let's say, IPv4 as well. It works very well with IPv6 through the multi-protocol extension. Oops, sorry, I went a little ahead there. The multi-protocol extensions capability built into BGP. There is so much to BGP that, we could probably spend a day talking about BGP theory, but we want to get some hands-on going. One last thing I will point out is with respect to BGP path selection process, there is the ability to control or influence the path you take through a number of different attributes. Now, we won't get into the details of that, but if we have some time, we can talk a little bit more at great length. Why we might want to do something like this, like influence the path. And here's a great example. If I'm using this diagram, this path from this router down to this router over here, there's two ways it can go. It can go through this iBGP pairing and through this eBGP pairing and then over here, or it can go take a longer route where it takes, one hop here and then another hop here. But here's the interesting thing. What if this link here was really slow, like it was a 10 meg link or something like that, while these two links here were, a gig link each. So you may not want to take the shortest path because it might be the slowest path, even though it might be a more direct path. Whereas if you take a longer path, it might offer up additional bandwidth that you can use so that your packet arrives at its destination in a much more quicker manner than taking the more direct path. So path influence is important there when it comes to deciding how you want to construct your BGP network. So we already know, what's the point here in, debating why BGP and Kubernetes, but BGP exists when it comes to CNIs and working with Kubernetes. There's a number of CNIs that support BGP functionality today. Cilium happens to be one of them, Calico is another, but we're going to focus specifically on Cilium today and understand a little bit of the architecture of Cilium and how it operates with BGP. So some of the key capabilities built into Cilium, basically, there's the BGP control plane. It can go about and advertise pod CIDR information. So if you have a number of nodes, each one of these nodes is going to have its own pod CIDR, its own unique pod CIDR, non-overlapping, because we've turned on BGP or we've enabled the BGP control plane. Now, these can get advertised to an upstream top of rack router, which would be aware of the different pods and their associated IPs running inside of your Kubernetes environment. But here's the reality, we're not always going to be directly interfacing with pods. We may interface with service IPs. And so with Cilium, you have the ability to create a load balancer service and then advertise those IPs, those service IPs, into the BGP process and basically be advertised to your upstream or your peers, your northbound peers. So let's just say, for example, this is your top of rack switch or top of rack router. It's going to learn routes about service IPs from the BGP control plane operating in Cilium. Now, there's a number of other features that Cilium provides. For example, it allows you to run eBGP multi-hop. So you might want to peer with a router that is maybe a few hops away, and so you can enable that when you configure your BGP peering policy. There's also another feature called graceful restart. Now, in graceful restart, one of the main considerations is to ensure that our data path is still available and we're able to reach remote networks, even if the control plane goes down. So there might be a situation where I have to upgrade my BGP control plane, or I'm basically upgrading Cilium, which might indicate that Cilium as a process is going to go down with the BGP process along with it. But in that situation, I shouldn't lose access to any of my services that exist inside of my cluster. So one of the ways to mitigate this and work around the situation is to turn on graceful restart. What it does is it indicates to the neighbor that it's going to be going down as a process, and for the neighbor to not remove or flush any routes that it knows about until a timer expires. So there might be a timer that says we're going to wait, by default, 120 seconds for BGP to come back online in Cilium. If it doesn't come back in 120 seconds, well, the neighbor is then going to flush those routes and mark them as unreachable at this point. They no longer will be available in the main routing table. Now, if BGP comes online within that 2-minute window or that 120-second window, the neighborship will get reestablished and the routes won't be pruned or flushed in any way. So basically your data path or your data plane should continue to function. You should still be able to pass traffic around without an issue. So we're going to see a little bit of how that works. I'll show you a quick demonstration, and then I'll show you how to set up BGP multi-hop as well. Also, as I mentioned, BGP supports IPv4, IPv6 capabilities. There's the ability to now create a load balancer IP address management pool so that you can create a pool and then assign addresses to any service that is instantiated inside of the cluster and pull an IP from that, which then gets advertised into BGP and shared with the rest of the network. One other thing that I'll point out is that you actually have support for multiple IPAM pools. So I'm going to pause there because I've been talking quite a bit. I'm going to pass it to Daneyon to maybe talk a little bit about that and maybe some of the other features that you've been working on.
Yeah, you bet. Let me share my screen really quick. Let's see, how about I just share my entire screen, share. Why can't I share my entire screen? Let me try it again. If you're going to cancel, make sure you click share. Okay, let me try present. Share screen. And that's not working. Can I share a window? That I can. Let's see which one. Okay, let's try this. Oh, nope, now I can share my entire screen. Cool. All right. You're able to see my screen okay? You can see my browser. So what we have here is a demo that I put together to demonstrate the integration of BGP control plane with multi-pool IPAM. And so this is a feature that's just hot off the press. It's not even documented yet, but it is this pull request 27100. and this added multi-pool IPAM support to BGP control plane. So as Marino mentioned, is BGP control plane can advertise different types of routes from within the cluster. It can advertise services of type load balancer. It can advertise pod siders. And now with this feature, it could also advertise pools, cider pools that are allocated to nodes from multi-pool IPAM. So if you're unfamiliar with multi-pool IPAM, take a look at the Cilium documentation for multi-pool. And at a very high level, what you do is you create the Cilium pod IP pool CRD or an instance of the CRD, and you create pool names, create um, CIDRs or subnets for each of the pool. And then the operator actually watches, Cilium operator watches this resource. And when pods get allocated to nodes, the operator will take a CIDR from one of these pools and allocate it to a node, and then the node assigns the IP to the pod. And there's a mechanism that I'll show you how you could actually specify which pool you want to use for your pod. So let's walk through this demo really quick. I've already done some of these steps that I'll show you as I've created a Kubernetes cluster using Kind. Cilium provides us some nice make targets to do this very easily. And as I mentioned, this feature is I think a week or two old, and so there's not a Cilium release. So like 114 does not include this feature. So instead, what I do is I actually build the container images for the operator and the agent, and push those images to my Kind nodes using this Kind image target. And then I install Cilium. And I install Cilium. The first step is I create the values that will be used by Helm. And you see that I'm setting my IPAM mode as multi-pool. And I'm creating a couple pools, Cilium pod IP pools, right from the installation here. And you see one is named default, the other is named other. They're IPv4 pools. And you see here that the pool is for default here is a 10.10.00/16. And what the operator will do is allocate /24 networks to the nodes when needed, right? And again, when is it needed? It's needed when there are pods that get scheduled to a node and either use, if the pod doesn't specify a pool, then it comes from the default pool. But again, I'll show you here shortly that there is a mechanism when you instantiate a pod or let's say a deployment or daemon set where you can actually specify which pool to allocate the IP for the pods. I enable BGP control plane here. And then some of these other configuration parameters go with BGP control plane. So I want to disable tunnel mode, specify what CIDR block that we'll use for native routing. And then this auto direct node routes is a slick feature within Cilium that allows the different nodes to automatically learn about the other pod CIDRs from the other nodes. I enable debug level logging. Just typically as a developer, I'm diving into all the detailed log messages. And then the operator and agent images is basically what it's saying here is just grab the image locally, because again, this make kind image not only builds the image for the operator and the agent, but then pushes it to the kind nodes. So, and then after creating that values file, we then just simply install Cilium using the values file, right? And we wait for Cilium to be ready. And to show you here, I've already gone through all these steps here, right? So we'll just backtrack really quick. Created the kind cluster. You see it's up, ready to go. Build and push the image to the nodes, and then create my values file and install Cilium, wait for it to be ready. Let me hide this really quick. All right, so back to the demo. The first thing we're going to do is annotate our nodes, right? And what this is doing is saying I've got get nodes. You'll see my cluster is simply two nodes. I've got a control plane and a worker node, and I'm annotating these nodes. This is what we do with BGP control plane to say, hey, node kind control plane, you are in autonomous system 65100, and you're going to use local TCP port 179 to listen for BGP peering neighbor relationship messages. And then I do the same thing here with the worker node, but the difference here is I'm using autonomous system 65200 and listening on the same port. And so when we go to form a neighbor relationship, you'll see here I create a Cilium BGP peering policy down here. And the peering policy, it's actually two different policies. One called CP for control plane, one called worker for my kind worker. Right? And as part of these policies, I use node selectors to select which node I want to apply these policies to. And so you see that the peering policy CP gets applied to kind control plane using this label. That's a default label that gets applied to a control plane node, and the same for the worker. Now, the other areas of these peering policies you'll see is that we create a single virtual router on each of these peering policies. We will not be exporting pod CIDRs, and that is because we're going to be exporting pod IP pools. And as part of this puller request that I showed you here, 27100, there's a new field within virtual routers called the pod IP pool selector. And this is a label selector that matches for labels. And we're going to be looking. So what we have here is we're telling this peering policy to match pod IP pools that are labeled as foo bar, right? And the other aspect of this that I don't want to gloss over is that we specify here for this policy the local AS of 65100, right, which matches how we annotated the node. And we created a neighbor that's in autonomous system 65200. That will be the worker node. And so what does this mean? This is an eBGP peering relationship between the control plane node and the worker node. Now, in a typical production environment, this isn't something you're going to see. This is just simply for demonstration purposes. So we've annotated the nodes, right? We would typically go ahead and do get nodes -OY so we can see that what IPs are assigned to the different nodes. So let me set my control plane environment variable saying the control plane IP is 16.2 and my worker IP is .3, so that when I create these BGP peering policies, we'll substitute these variables with the actual IPs of the nodes. So let's go ahead and create the peering policies. And we'll look at the peers. And Marino touched on this earlier about the state of peering relationships. You see that they're in an active state right now. So that means that these two BGP speakers will not be sharing any network layer reachability information, right? So they will not be saying, "Hey, kind control plane, here's here's a network that I know of," and vice versa. That does not happen until established is achieved. And you may be saying to yourself, well, okay, we have a session state of established. Why don't we have any routes being advertised, right? So if I created this peering policy and it gets applied to the control plane node here, right? We want to advertise routes to our peer, which is the worker node. But right now, the only thing that would be advertising is CIDRs from this pod IP pool that matches labels foo bar. So if we get Cilium pod IP pools, well, there's no labels here, right? So there's nothing to advertise because there's no IP pools that match the label selector that we specified in our peering policy. And again, here, this is even why the demo shows you here, like nothing's being advertised, but first things first, we have a neighbor relationship established. So we're off to a good start here. And again, I show you here in the demo, no labels on any of the pod IP pools. We could even do the same for the other pool, right? No labels. So we need to go ahead and label one of these pools so that we start advertising routes. We see that the pool, our default pool, is now labeled. And the kind control plane node is advertising the pool, or we at least assume that it is, right? We just know that it's advertising one network, and the worker node is receiving one network. So what we can do is, before I do that, get nodes, or get PO, and we're going to exec into the kind control plane node and take a look at the route details that are being advertised, right? So we know kind control plane is advertising a route. We don't know the details of the route just yet, but let's take a look at that really quick. So we're going to exec into the control plane node, specifically the Cilium agent container within that node. And we're going to issue the Cilium BGP routes advertise IPv4 unicast for peer. All right, so the peer is the worker, kind worker, so the peer would be 16.3. And here you go. So 10.10.0 network is being advertised, and you see the next hop being the kind control plane node. And these steps confirm the steps we just took. And now let's go ahead and do the same thing for the other pool. Pretty simply, just label that pool with the same foo bar label. See that the peers, oh, wait, what happened here? How come we still only see one advertised route and one received route? How come this is not being updated? Well, it's more than just labeling the pool. There needs to be CIDRs that get allocated to nodes. And since if we look at Cilium node, and if we look at the kind control plane, it only has a CIDR from the default pool. Well, why is that? Because there are no pods that have requested an IP from this other pool, which just makes sense, right? Why would we want to advertise a route when there really are no endpoints associated to that network, right? Traffic would get routed there, and then typical networking, if there is no endpoint, it's gonna not traffic's not going to go anywhere, right? So what we can do here is we can go ahead and create a daemon set that requests to use that pool. And so you annotate the pods with this well-known annotation that specifies what pool. And since we're talking about the other pool, we specify the other pool. So let's go ahead and create this daemon set. And let's wait a second here for the pods to come up. While we're doing that, I'll show you here is you'll actually see, since the other pool is a 10.20 network, you'll see that because this is a daemon set, each pod gets scheduled to a different node, one to the control plane node, one to the worker node, and each of these nodes will have a CIDR allocated from the other pool, which is a 10.20.0016. Let's see here. Again, just like what you see in the demo, the 1020 network. And now if we go back to the node, the kind control plane node, we now have the other pool that gets allocated, right? We needed for the operator to allocate a CIDR from that pool in order to allocate this IP address to this netshoot pod, right? And now what do you know? Now we're advertising that network. And we can do the same that we did before and verify that that second advertisement is the 10.20.00/24 network. And this confirms the steps that we just took. And if you're interested in learning more, you can follow these same steps for the worker node, right? So everything you've seen so far is the control plane that's advertising these routes, and that the worker is receiving those routes because these two have an established neighbor relationship. You can go back and follow the basically the same steps to do for the worker node to advertise the pod IP pools that were assigned to it. And if you're interested, I don't know if we want to go through it now. Maybe you could circle back to me, Marino. But there's another feature that just landed in BGP control plane as well, that Ratislav Zabo, I apologize if I'm mispronouncing your name, but he added advertised path attributes to the Cilium BGP neighbor field. And this allows us to take advantage of some of those BGP attributes to modify how routes are preferred amongst BGP neighbors. And so, Marino, I can hand it back to you. We can go through the second demo if you'd like, or
that's good. Thank you so much.
Mm-hmm.
So I'm going to flip over to my screen now because I've also got a little bit of a demo that I'll share with y'all. And I'm going to go ahead and just remove Daneyon's. I'm going to go ahead and present my entire screen here. Actually, no, I should just do window. Okay, so we've had a look at the BGP control plane in action. We're going to see a little bit more of it. I just wanted to point out how BGP functions in Cilium, in that anytime we have the BGP control plane turned on and we pass a BGP or a Cilium BGP peering policy CRD resource over to Cilium, the agent will always watch for that. Once it sees that, it'll basically look at what the Cilium BGP virtual router configuration looks like, and we'll go on to implement a Cilium BGP virtual router, which is what is effectively interfacing and neighboring with anything upstream. So you had a look at the BGP peering policy. I'll come back and revisit this in the demo because I can point out some specific configurations. In our demo environment, the one that I'm going to show you right now, I've got a setup where I've got 2 FRR routers, free range routers that are deployed as containers. Oops. And if you actually see here, this red line is representative of a network. So I've got a Kind cluster, 3-node Kind cluster running some Nginx pods. And the nodes on this cluster are directly on the same network as this interface of this FRR router. At the same time, we've also got another FRR router here on the left, which is supposed to peer and neighbor or just be on the same network as this FRR2. Now, the reason I have this set up is because I also want to demonstrate multi-hop connectivity, or how we can establish a BGP peer through a hop. But what I'm going to show you first is graceful restart in action, and how I should still be able to access my Nginx pod, even though the BGP control plane might be restarting on this FRR router. So let's take a quick look. I'm going to stop sharing my screen here, and I'm going to share 2 windows. I'm going to share 2. Share screen. Window. Let's see. Okay, you can only see one of them. Actually, you're looking at the wrong one right now. That's fine. I actually want to show you another one. You know what? It's probably just easier to share my entire screen, and then y'all can take a look and see what I have running. Okay, ignore the screenshots on the right-hand side. I am one of those people that have bad habits when it comes to organizing my screenshots. Every once in a while, I'll dump everything into an untitled folder and then try to figure out where I made that screenshot, but you can ignore that for now. Okay, so I've got a couple of things going on here. If I do a kubectl get nodes wide, we know that we've got a 3-node cluster here, and we know these node IPs. If I run a Cilium status, Cilium is already up and online. The BGP control plane has been enabled, so I don't have to go in and turn that on. And what else? If I actually do a Cilium BGP peers, you'll notice that nothing is there right now, and that's because I don't have a BGP peering policy set up at the moment. Now, over here, right, I'm just going to exit, and I'm actually going to terminal into this router, Tor FRR2. And if you want to take a look and see the configuration, we can show run. It's very similar to a Cisco iOS CLI in a lot of ways. So we were able to see some familiarity there. But if you notice, the core configuration lives here under my router BGP process. So I've defined my ASN, which is 65,012, which is locally significant to this router, or locally configured for this router. We've got a BGP router ID assigned to this router, and we've got a number of neighbors that have been configured. This neighbor here is the Tor FRR1, which is over to the left of this Tor FRR2. And then the rest of these neighbors, they're actually just 3 neighbors here with just multiple configurations. These are the Kind nodes. Now, one thing I will point out is, if you notice, each one of these neighbors has this line, graceful restart. So as I mentioned previously, graceful restart will effectively allow you to restart the BGP process without tearing down any routes. So if I do a show IP route right now, I'm not learning about any BGP routes at the moment. We're going to fix that in a second. Also, I have this little container, Docker container that's running off to the side. And it's, if we look back at the diagram for a second, where's that diagram hiding? No, not that one. Actually, this one is fine, but I'll just bring up the slide deck again. So if we look at this diagram here, this net chute is actually on the same network that sits between these two FRR routers, which means it's going to have an IP address on the same network. Now, if we look at any one of these, right? Let's look at this for a second. If we do a ifconfig, we'll notice that it's got an address of 172.20.05. If we decide we want to bash into one of these containers, let me exit out of here and then type in bash. And if I did an ifconfig, notice that it's got an interface 172.20.03 on ETH0. So I technically should be able to ping that netshoot container. Oops, 172.20.0.5, and it's going through fine. Now, there is some slight hack I will have to do here, because anytime we spin up a container, the default route is assigned by the bridge, and it happens to be the bridge. So any default route traffic would go to the bridge, and it might not know where to direct that to. The challenge is I can't sit there and configure the routing specifically for the bridge. So we have to manually create some static routes that tell netshoot how to reach the rest of the network in certain ways, because we can't just simply specify the BGP speaker as its default gateway. Now, let's go ahead and set up our BGP peering. So I've got a BGP peer policy here. We're going to apply this. Okay. And at the same time, if we go into here and we do a show IP BGP summary, we'll start to see that neighborships are being formed and we're receiving messages. But if we also look at show IP route, now we're actually learning about the BGP routes. We're learning about a few of the routes. In fact, 3 of these routes, right? 10.242.0.0/24, 242.1, 242.2. These are the node level pod CIDRs. So like Daneyon was showing you earlier on, when we looked at each node, there was a CIDR allocated for that node. That's where that CIDR is coming from. So these CIDRs get advertised into the BGP process, because guess what? Any pod that lands on this particular node will pull an IP address from this IP address range here. There's also one more route, which we're actually learning about through 3 ways, and this is the service route. So this is the service IP of a system of the Nginx pod. In fact, if we go back here and we did a kubectl get svc, we can see that this external IP has been advertised into the BGP process, so it can show up on the FRR router here, the Tor FRR2. Okay, so what this should mean is when I previously ran this curl command, I should have been able to not have access to the application. But now that I've set up BGP routing between the 2 environments, between FRR as well as kind, I should be able to curl this app, and I can access Nginx that's sitting on the other side. So this is good. What happens if we have to restart the BGP process due to an upgrade, or something of the state of something failed and the control plane is down? So what we're going to do is we're going to take down the BGP control plane. We're going to verify that the routes are still there. We're going to verify that we can still run a curl. So the way to do this is we're going to do a kubectl -n kube system rollout restart daemon set Cilium. And the moment this occurs, right, this is just basically a restart of the pods. And effectively, that should tear down the BGP neighborships, but that shouldn't tear down the routes. So the Cilium agents have been rebooted. My routes are still there. If I do a show IP BGP summary, or I can't remember, show IP BGP summary. So, oh, here we go. You see that the state is set to active. that means that the neighborship isn't established anymore, but the data path should still be functional. So the other thing that's a dead giveaway is that if I look at my routing table, everything is still functional. Everything still looks good. If I look at Cilium BGP peers, now everything is established. But look at this. Look at how long it's been online for. It's only been online for less than 30 seconds, 30 seconds or less per peer. I'm going to rerun that restart command because I didn't give us enough time to actually test out whether or not the curl would still function. So I'll run this command again. I'll double check that the BGP peers are down, which it's down. And if I curl now, it still works. Still works. Still works. So what this has told me is that despite BGP gone down, despite the fact that the control plane is offline, the data path or the data plane will still be or available, and we can still route traffic. What we've just effectively done is that Cilium, or the Cilium BGP process, has told its neighbors, which is Tor FRR2, that it's going down. And it's going down, and to wait 120 seconds before before the neighbors decide we're going to flush the routes and mark these routes as unreachable. Once BGP comes online before that 120-second timer expires, everything stays the same, so there's no route reconvergence that's required. So if I rerun the Cilium BGP peers, everything's established again. I've been talking for about a minute. Curl still works. That's all good. The next thing we're going to do is we're actually going to remove this Cilium BGP peering, and we're going to just demonstrate some quick multi-hop BGP. So if we look back at the diagram, currently as it stands, oops, that's too quick. Currently as it stands, this FRR router can peer directly with this kind cluster, meaning they're exchanging routes, no problem. This FRR router here has two options. It can peer with this FRR router upstream and learn about those routes through FRR2, or it can do multi-hop to basically establish a peer relationship directly with the kind cluster. Now, in order for this to work, we actually have to make sure there's IP reachability between Tor FRR1 and its interface and the kind nodes IP interfaces as well. I've already established that. The way you can establish that is either through an underlying routing protocol like OSPF, or you can just plumb some static routes. Obviously, in a lab environment, static routes happen to be the most ideal approach. But when it comes to production, you probably want to be using a more specific routing protocol to help with this. Now, let's go ahead and delete. I have the command somewhere here, so let's go ahead and delete the graceful restart. I'm going to up arrow and just change this to multi-hop. And I'm just going to go to the front of this command, or the beginning of this entire line, and just do an apply. And now if I do kubectl, and I'm going to just minimize this. I don't want to do a kubectl. What am I talking about? If I do a Cilium BGP peers, right, we're establishing a fresh new set of neighborships. But look, because I have the previous output here, notice that the BGP peer address has actually changed. It's not 172.21.0.5. It's actually 172.20.0.2, which actually is the interface that is facing us, but from Tor FRR1. So this is also the router ID of Tor FRR1. Because I've applied this multi-hop peering policy, if I go over to Tor FRR1, if I do a show IP BGP neighbors, actually, I'm in the wrong router. I apologize. I have to exit out of here. I'm going to clear my screen, and I'm going to shell into Tor FRR1. So if you look up here, right, BGP neighbor is 172.21.0.3. Remote AS is 65.01. Local AS is 65.0.13. And then local AS is 65,011. I am peering. We know that the neighborship is online because I should be able to see an established message somewhere here, and I'm not finding it. Oh, here we go. Connections established 3, which means that we are peering with kind. And if I do a show IP route, I will be learning about those routes. So in fact, I'm going to learn about the routes 2 ways. And the reason why this might be occurring is because of BGP and the way I set it up as a peer with Tor FRR2. But I think the one thing that we want to pay attention to is how the service address is being learned. So the service address 10.12.115.45/32 is being learned through 172.20.03. Who is 172.20.03? That's actually the BGP peer Tor FRR2. But also, if we look at the line right above, this is actually the node, the kind node, one of the kind nodes actually. And if we look further down, there's another kind node. There's another kind node. And then these are the pod siders that are advertised to BGP from the kind nodes themselves. So what this is telling me is that I can go ahead and establish a multi-hop peering between 2 geographically separate routers, provided that I do have IP connectivity between them, even though there might be some hops in between, some router hops in between. So I'll just show you the brief configuration of this so you can kind of familiarize yourself with this. There's a eBGP multi-hop subcommand that's been provided under the BGP process here. And all it's telling is that this neighbor is multiple hops away. We don't know how many. We could specify that if we wanted to, but it assumed that it could be up to 250 hops away. And 255 is actually a TTL to expire it so that we don't have neighborships looping around the network. Now, if I'm going to stop sharing this. I'm going to just reshare something here. If I take a look at this example, right? By the way, you all can go here and follow along exactly as what I've been showing you here. Everything that you follow here will get you the exact same environment in terms of functionality. It's a little different from Daneyon's environment only because I am using multiple routers and I'm using FRR. And I think in your previous environment, Daneyon, you use the Bird router, right? Yes, you do use the Bird router. All right.
Yeah, just a little different process, but
yeah, there's a few configurational elements that you might change. In fact, the way you configure your routers will be different. I just like to think that FRR is a lot more like iOS or the iOS CLI because of the familiarity of being able to just run into or get into config mode and then be able to configure BGP subprocesses. But anyways, this entire document will walk you through how to get your kind cluster deployed, the 2 FRR routers deployed, the required Docker networks to make sure that we have that similar topology that I displayed to you. And I'll update this repo with that topology diagram as well so you can leverage that for your own usage. But more specifically, what I wanted to show you in the BGP configurations here, right? So these two are the very same. One is just specific graceful restart, doesn't have multi-hop, and the other one has multi-hop enabled. So walking through this, we've got a name. What we want to make sure of is the node selector here. We can assign other labels to nodes, and we can actually have multiple BGP peering policies doing different things, but this can only occur on a per node basis. So if you have multiple BGP peering policies and they're covering multiple nodes, I believe it's the previous one or the first one that you've deployed which takes precedence. Correct me if I'm wrong there, Daneyon. So if I actually had one BGP peering policy deployed and then I decided to deploy another one on top with the same node selector, the first one that's deployed should be the one that takes precedence, right?
it should. I believe
Yeah.
there's actually an issue out there. I have yet to test it
Okay.
of potentially having a second policy that would select the same node if no policies would then apply. And if that's the case, that almost becomes like a denial of service attack. But
Okay.
let me find that issue and pop it in the chat window.
Awesome.
Um,
Yeah. All right, a couple of other things. So we've defined our neighbors. We know this is eBGP because our local ASN is different from our peer ASN. If they were the same, it would be an iBGP peering relationship. We specified our peer address, and then here's the multi-hop TTL flag that I've set. So right now, if this was set to 1, what would happen? If it was set to 1, this would just assume that my peer is directly connected. But because I've set it to 2, it is basically telling the BGP process your neighbor is actually an additional hop away. So you'll have to take one hop and then another hop to get to that neighbor. So you can define this and tune this accordingly. And then there's the graceful restart as well. We enable it, set it to true, and then we can actually modify the timer. So this timer can actually be less if we wanted to. And these timers get advertised to their peers as well. So feel free to come into this repo, copy it, fork it, whatever you want to do, make it your own, do whatever you'd like, and feel free to come back and ask us questions on it. So that being said, let me just finish off the presentation. We talked a little bit about BGP capabilities, showed you a couple of demos around multi-pool IPAM, and that's something that Daneyon showed you. He talked a little bit about the advertised attributes. This might be a great segue to talk a little bit more about that, right, Daneyon?
I'm sorry, I was just typing in the chat window about the comment has failed to post. Oh, I don't know why that comment failed to post. Weird.
That's okay. So I was just saying this might be a great time to jump in quickly to talk about the advertised attributes capability. I don't know if you want to.
Yeah, sure. Let me. Can you? All right. Stop screen. Let me present here. And why can't I share my screen again? I'll show you. It was canceled. Make sure. Let's try it again. Present. Share screen. Let me start off with just a window here and go from here.
There we go.
Yeah, so I mentioned earlier that this PR 27705 from Rastislav Rostislav Zabo, again, sorry, Rostislav, if I'm pronouncing your name improperly, but this adds advertised path attributes to the Cilium BGP peering policy. And I actually put together, here's the issue too. Here, maybe I could send it to you, Marino. And
Drop it in Slack, and I can drop it into.
Yeah, if you could for me. I don't know why that was having some problems. But yeah, this is an issue that when it came across the radar when I was going through the BGP documentation, just concerned me a little bit because from my understanding is if you inadvertently applied a second Cilium BGP peering policy to a node, that the node would actually flush all BGP peering policies. And I think what I basically state here is we should support multiple policies and ensure that there's some mechanism for conflict resolution. And this is essentially what I propose to the community. And I think it's just gone stale. So it's something that hopefully gets readdressed here and see where we go from there. But anyways, let me close that out and go back to a demo that I have of route policies. And I'll kind of explain the route policies as we go through this demo, and I'll be a little bit quicker since we're running out of time. Just like the demo that I shared with you earlier before, I've got a client cluster. Since this is a new feature, I had to use the image build target to build Cilium operator and agent and push the image to the kind nodes. It's a 2-node cluster, control plane and worker. This time, you'll see that the nodes are in the same autonomous system, 65100. And that is because in this peering policy, what I'm going to demonstrate here really quickly. So after I went ahead and created the cluster, I installed Cilium. And when I installed Cilium, this time I'm just using the Kubernetes IPAM mode, where in the last demonstration, that was for the multi-pool IPAM. And everything else is pretty much the same. I'm building the images, so they're expected to be local, and then doing native routing instead of tunnel. And I install from that values file, wait for Cilium to be ready. Cilium's ready, and so now I annotate my two nodes again using the same autonomous system number of 65100. I get the node IPs that I'll use for my BGP peering policy, because I'm going to go ahead and peer between the control plane and the worker nodes. All right, so I get the IPs, set my environment variables that I'll use in the peering policy. And here's the peering policy. Let me go ahead and apply it. And it's a peering policy, two of them, CP for control plane, worker for the worker node. And you see here that the control plane node is this time advertising pod siders, right? And it will also advertise services of type load balancer that match this label. So we need a service to not only be of type load balancer, but it would need to be labeled app nginx for the V router on the control plane node to advertise that particular service. Again, the basic configurations of the local AS number, the peer AS number. Again, this is going to be an iBGP neighbor relationship, since they're both part of the same autonomous system. I specify the peer address of this particular neighbor, and this is the new functionality that was added in the pull request that I just showed you, and that's the advertised path attributes. Right, so the power of BGP is not only just advertising routes, but it's being able to have metadata associated with those routes, so that when a BGP speaker knows how to get to a destination from multiple peers, that it can use some of this additional metadata to pick which is the preferred path to get to that destination network. And what we are doing here with the advertised path attributes, we're saying, okay, we're going to select the load balancer IP pool that matches this particular label, just like what we did in the last demo, where we're using label selectors to match pod IP pools. Same mechanism here to match load balancer IP pools. And what are we going to do for routes that match this selector? We're going to go ahead and add the standard communities of 65001:100. And then we have a different selector as well for this neighbor, where we're going to say we're going to use a pod sider selector. And we're going to say for any pod siders, we're going to apply the local preference of 150. And so let's go back to the demo here. And one of the first things we're going to do is, hey, is the peering relationship up? Let me hide this. And we see it is. Our peers are established, and the control plane is advertising one prefix, and the worker is receiving that prefix. And so we can go ahead and exec into Cilium.
So Daneyon, we can't see your if you're sharing.
Sorry about that. That's because it was only allowing me to share my one screen. Let me stop screen sharing. Let me try again. Present, share screen, entire screen. Now it's still not. Yeah, I don't know. It's just not letting me share my entire screen. Let me jump to a window then, and let me go back to this window, and you can see this, right? You can see my screen now?
Yep, I can see it.
Okay, and let me just recap, I apologize. Forgot I was only sharing my tab for my browser. But just to recap, I created a kind cluster. I built the Cilium uh, binaries and wrap them into the operator and the agent Docker images. And I went ahead and I created a values file, the values that will be used by Helm for the install. And I set all these values here, which basically say use the Kubernetes IPAM mode, enable BGP control plane, and then pull the agent and operator images locally. Because again, I built and pushed those images to my kind cluster nodes because the feature that we are demonstrating here has yet to be included in a Cilium release because it is a brand new feature. After the install, I wait for Cilium to be ready. We see that it's reporting ready. I annotate my nodes. Again, I'm annotating these nodes with the same autonomous system number of 65100. My control plane and worker will be iBGP peers. I create that peering relationship by using the Cilium BGP peering policy custom resource. I create one for my control plane node. You see I named it CP, and it is matching these node selector labels. And this is a label that is a default label that gets applied to the control plane node, and the same for the worker node. What you see here is with the peering policy for the control plane node, I am peering with the worker node, and I'm using this new field that we're focusing in on for this demo, and that's the advertised path attributes, right? And so the advertised path attributes has different selectors. This is a Cilium load balancer IP pool selector, and it will select IPs from any Cilium load balancer IP pools that are labeled with foobar. There's another selector type that we'll use for advertising prefixes to this neighbor, and that is the pod cider. And we're going to apply the local preference of 154 prefixes for pod cider prefixes. And you see here that when I applied these two peering policies, we have established a neighbor relationship between the two nodes. And let me go back to the demo here. And you can't see my screen since I'm not able to share my entire screen. But what I'm going to do here is I'm going to exec into, let's see here. So let me get PO-M, and I'm going to Cilium. So I'm going to exec into the control plane node. Let me get the control plane node here. And we are going to look at the details of the routes for this peer, right? So we're execing into the control plane node, right? And into the Cilium agent container and issuing the Cilium BGP routes advertise IPv4 unicast peer and the IP of the peer, and that peer is our worker node. And we see that we are advertising this prefix, which is the get Cilium node control plane. Where is Podsiders? There it is. The 10.244 network, right? So with the IPAM mode Kubernetes, all pods that get instantiated on this node will get an IP from this CIDR, and you see that that matches the prefix that's being advertised with the next hop of the control plane node. But the key is right here, is right, again, BGP, it's more than just the network layer reachability information, right? The prefixes that get exchanged between neighbors, but it's some of this additional metadata. And one of the pieces of metadata for a path is a local preference. And this is an attribute that is specific to iBGP peers. And that's why the kind control plane and kind worker nodes are iBGP neighbors instead of eBGP neighbors, because this is an attribute that does not get passed to eBGP neighbors. And local preference is just a mechanism within BGP to prefer this route over other routes. So so if I was a BGP speaker and I learned about this prefix through multiple different neighbors, but one had a higher local preference than the other, I would prefer the one with the higher local preference. Now, the next thing I'm going to do is I'm just going to quickly go ahead and run a sample application so that we can see the other part of the path attributes that we can manage. Let's wait for the Nginx deployment to be available. But what I'm teeing up here is, if we go back to the peering policy, right? What we just demonstrated here was that the control plane virtual router will advertise the pod CIDR block with a local preference of 150. Right? We just saw that. But the other part of the peering policy is the Cilium load balancer IP pool selector that says any IPs from a Cilium load balancer IP pool, the pool needs to have this label. We're going to go ahead and add the standard communities attribute. Okay, and so we've got the pods in the daemon set running. In the demo, I verified connectivity within the pods. I'm going to skip that just because we have time. I know because I've done this enough that that is established. But what I'm going to do now is I'm going to create that Cilium load balancer IP pool. You see that it has the foo bar labels, and I specify the CIDRs, right? So when I go ahead and I expose my Nginx deployment as a service of type load balancer, and I label it here, app Nginx, right? If we go back to the peering policy, you see that the peering policy, we tell the control plane virtual router to go ahead and advertise any services that match a particular selector, right? Match labels app Nginx. And if we go here, we see that I labeled the service with app Nginx. So BGP control plane on the control plane node should start advertising this service. And you see which IP it should be advertising is a get service Nginx. What the Cilium load balancer IP pool did is it went ahead and assigned this external IP. Right? Without this Cilium load balancer IP pool, it would be waiting. We would never get an IP for this pool. So it's these two features working together, right? IPAM, this one in particular, is a load balancer IP pool, and BGP working together. So the service gets an IP from this pool, and then BGP, we told BGP that go ahead and match any IPs from a Cilium load balancer IP pool, as long as that pool has this label foo bar. And again, let me just go back and show you once again to help connect these dots, right? So this is what we're talking about here in the BGP peering policy. And when that match occurs, any prefixes go ahead and apply the standard communities here. So if we go back and now look, here we go. So the control plane is advertising the two prefixes, just like the one we saw before from the pod cider, but now the Cilium pod IP or Cilium load balancer IP pool, right? This IP 117 here that came from this pool is now being advertised via BGP. And here's the key right here that I wanted to show you. Here's the path attributes that get applied. And again, this is just another attribute that allows BGP to differentiate preference of, how to prefer routes when there are different peers and a BGP speaker is learning the same prefix from different peers, how to prefer one prefix over the other, and then add that to the route table. And I think that's about it.
Awesome. That's great. Okay, let me just present one last slide and I'll summarize everything. The slide that I'm going to share is actually not going to be a summary slide, but I just want to point you all to a resource called Solo Academy. But the reason I bring this up is because to better understand some of the networking, to better understand how all of this works, it's always great to dig into some of the foundational stuff as well. So if you head over to Solo Academy, there's a Network Foundations course that I built about a year ago that gives you some of the basics around understanding DNS, IP routing, understanding how that all fits with Kubernetes, and understanding things like network namespaces and whatnot. And then what you would want to do is then go on to take our Cilium workshop, which actually brings you to the level of understanding how Cilium works and how it functions. And then once you've gotten past that point, any one of the repos that either Daneyon or I have shared should be more than adequate to get you to the point to get a working BGP configuration running. Obviously not for production, but for lab testing, understanding how things work within Cilium and BGP. So just to summarize, we covered off what Cilium is, what it does, especially how it relates to Kubernetes and how it works inside of Cilium. You know what? Let me reuse one of the slides here. We also reviewed how it's a path vector protocol. It supports iBGP or eBGP capabilities, and how specifically within Cilium, we have the capabilities to advertise pod siders, service siders, peer with top of racks, routers or switches that can run BGP, enable things like graceful restart so that we can accommodate for upgrades in our environments or any sort of situation where the control plane has gone down, and then also accommodating for other kinds of scenarios where we might need multiple IPAM pools, or if we're trying to advertise specific paths or attributes to understand how we can route around the network. So there's a lot that BGP can do in Cilium today, and we hope to uncover more and dive deeper into the BGP control plane and BGP with Cilium in future sessions. So just want to say thank you all so much for joining today. I really appreciate you showing up to this Hoot event. I know it was a little bit longer. I also want to thank Daneyon for showing up and showing some amazing stuff around BGP, and also behind the scenes helping me a lot with understanding how BGP and Cilium work. So thank you, Daneyon. Go check out the show notes. We'll share them very later on in the description of this video, and then you should be able to copy everything we've done here. I hope to see you at the next Hoot. Thank you so much, everyone. Take care.
Thank you. Bye.